Fusion is the fundamental process that powers stars, including our Sun. It is responsible for the immense energy output of stars, the synthesis of heavier elements, and the overall stability of stellar structures. At its core, fusion involves the merging of atomic nuclei to form heavier elements, releasing vast amounts of energy in the process. However, for fusion to occur, specific extreme conditions must be met. These include incredibly high temperatures, immense pressures, sufficient particle densities, and the presence of strong gravitational forces. This document explores in detail the essential conditions required for fusion in stars and how they contribute to stellar life cycles. One of the most critical conditions for nuclear fusion is temperature. The core of a star must reach temperatures of at least 10 million Kelvin for hydrogen fusion to begin. These extreme temperatures provide the necessary kinetic energy for atomic nuclei to overcome their electrostatic repulsion, known as the Coulomb barrier. In the Sun, core temperatures reach approximately 15 million Kelvin, enabling the proton-proton chain reaction. More massive stars, where heavier elements undergo fusion, require even higher core temperatures, reaching up to hundreds of millions of Kelvin in supergiants. In addition to high temperatures, a sufficient density of particles is essential for sustaining fusion. The core of a star must have a high enough density so that nuclear collisions occur frequently. In the Sun, the core density is approximately 150 times that of water, creating a suitable environment for fusion reactions. The immense pressure generated by the star's outer layers also helps to maintain these densities. This pressure results from the gravitational force acting upon the stellar material, compressing the core, and ensuring that the necessary conditions for fusion are maintained. Gravity plays a fundamental role in enabling fusion by providing the confinement necessary to sustain high temperatures and pressures. As a star forms, gravity pulls vast amounts of gas and dust inward, compressing the core and heating it to the necessary temperatures for fusion. Without gravitational confinement, the core would not be able to sustain the conditions required for fusion, and the star would dissipate. Gravity also ensures that once fusion begins, the energy released counteracts the inward pull, stabilizing the star through a balance known as hydrostatic equilibrium. Even under extreme conditions, nuclear fusion is made possible by quantum mechanical effects, particularly quantum tunneling. The Coulomb barrier, which arises due to the electrostatic repulsion between positively charged nuclei, would normally prevent fusion from occurring at the observed temperatures in stellar cores. However, quantum tunneling allows nuclei to overcome this barrier by probabilistically passing through it, rather than needing to overcome it classically. This effect significantly enhances fusion rates and ensures that stars can sustain their energy output over long periods. A star remains stable for millions to billions of years due to hydrostatic equilibrium. The balance between the inward gravitational force and the outward pressure generated by fusion energy. If fusion slows down, gravity causes the core to contract, raising the temperature and pressure until fusion rates increase again. Conversely, if fusion rates increase too much, the outward radiation pressure expands the core, reducing the temperature and slowing fusion. This self-regulating process allows stars to maintain a steady energy output over their lifetimes. Once energy is generated through fusion, it must be transported outward to be radiated into space. Two primary mechanisms enable this: radiation and convection. In lower mass stars, including the Sun, the core's energy is transported primarily through radiation, where photons carry energy outward in a slow process due to repeated absorptions and emissions. In more massive stars, convection dominates, where hot plasma rises and cooler plasma sinks, efficiently moving energy outward. The mode of energy transport depends on a star's mass and composition, influencing its overall structure and evolution. Stars undergo different types of fusion reactions depending on their mass and core temperatures. The proton-proton chain occurs in stars like the Sun and involves hydrogen nuclei fusing to form helium. It is dominant in stars with masses up to about 1.5 times that of the Sun. More massive stars use the carbon-nitrogen-oxygen (CNO) cycle to fuse hydrogen into helium, a process that requires higher temperatures but is more efficient than the proton-proton chain. When a star exhausts its hydrogen, it begins fusing helium into carbon through the triple alpha process, which occurs at temperatures exceeding 100 million Kelvin. In the most massive stars, elements such as carbon, oxygen, neon, and silicon undergo fusion, leading up to the formation of iron, beyond which fusion is no longer energetically favorable. The mass of a star determines the fusion reactions that take place within it. Low-mass stars, like red dwarfs, burn hydrogen at slow rates through the proton-proton chain and can remain stable for trillions of years. Sun-like stars sustain fusion for billions of years, eventually evolving into red giants and later white dwarfs after helium fusion ceases. Massive stars undergo successive stages of fusion, synthesizing heavier elements up to iron before ending their lives in supernova explosions or collapsing into neutron stars or black holes. Fusion continues in a star until it reaches iron, beyond which fusion is no longer energy-producing. At this stage, the star's core collapses under gravity, leading to different end states depending on mass. Low-mass stars shed outer layers and leave behind white dwarfs, while high-mass stars undergo supernovae, resulting in neutron stars or black holes. These processes enrich the universe with heavier elements, essential for planet formation and life. The conditions required for fusion in stars involve a delicate balance of temperature, pressure, density, and gravitational confinement. Quantum mechanical effects like tunneling further enable fusion at stellar core temperatures. This process not only sustains stars throughout their lifetimes, but also plays a crucial role in cosmic evolution by producing elements essential for the universe. Understanding these conditions gives insight into the past, present, and future of stars and the galaxies they inhabit.